LeetCode 3702, longest subsequence with non-zero bitwise XOR. At first glance, this looks like a subsequence problem. So you might think, let's try different subsequences and calculate their XOR. But with up to 100,000 elements, that approach is completely impossible. Here's the interesting part. We don't actually need to find the subsequence. We only need to answer one question. Can we keep almost everything and still make the XOR non-zero? And once you notice what XOR does when you remove just one element, this medium problem becomes surprisingly simple. Problem breakdown. We are given an integer array. We can choose any subsequence, meaning we can remove some elements while keeping the remaining elements in their original order. Our goal is maximize the number of elements we keep while making their XOR non-zero. For example, 1, 2, 3. The XOR of the entire array is 1 XOR 2 XOR 3 is equal to 0. So we can't keep all three. But if we remove 1, we get 2, 3. 2 XOR 3 is equal to 1. That's non-zero. So the answer is 2. Maximized length XOR must be non-zero. The key is that we're maximizing the length. That means we should remove as few elements as possible. Let's start with building intuition. Let's start with the simplest case. Nums equals 2, 3, 4. Calculate the XOR of the entire array. 2 XOR 3 XOR 4 is equal to 5. That's already non-zero. So why remove anything? We don't. We can keep all three elements. Therefore, answer equals 3. Now consider 1, 2, 3. The total XOR is 1 XOR 2 XOR 3 is equal to 0. So keeping everything doesn't work. But here's where we should think about the objective. We want the longest valid subsequence. If the entire array fails, what's the smallest number of elements we can remove? Just 1. Let's remove 1 frowny face 2, 3, and 2 XOR 3 is equal to 1. Perfect. So the answer is N1. But wait, can we always remove just one element and make the XOR non-zero? Not always. Consider frowny face 0, 0, 0. The XOR is 0. Remove any one element frowny face 0, 0. Still 0. Remove another frowny face 0. Still 0. So there is no valid non-empty subsequence. The answer is 0. And now we've reached the key observation. Why the obvious approach fails. The obvious solution is to generate subsequences. For every possible subsequence, calculate its XOR and keep the longest one with a non-zero result. But an array of size n has up to 2 power n. Different subsequences. With n equals 100,000. That's obviously impossible. Even a more clever dynamic programming solution would be unnecessary here. Why? Because we're not really being asked to construct some complicated subsequence. We're asking for the maximum possible length. That changes everything. Instead of asking, which subsequence should I choose? We can ask, can the entire array work? If yes, we're done. If not, can I fix it by removing exactly one element? And XOR gives us a beautiful property that makes this possible. The key insight, XOR equals 0. Here's the key observation. If the XOR of the entire array is non-zero, keep everything. Obviously, the answer is n. But what if the total XOR is 0? Now suppose A1 XOR A2 XOR, XOR AI XOR n equals 0. What happens if we remove AI? The XOR of everything else becomes 0 XOR AI. And because 0 XOR x equals x, the new XOR becomes AI. So if the removed element is non-zero, the remaining XOR becomes non-zero. That's the entire trick. For example, frowny face 1, 2, 3. 1 XOR 2 XOR 3 is equal to 0. Remove 1. The remaining XOR is 2 XOR 3. Because the original total was 0, this is effectively 0. XOR 1 is equal to 1. Non-zero. So removing any non-zero element fixes the XOR. Let that sink in. We don't care which non-zero element we remove. We only need to know Does at least one non-zero element exist? If yes, we can always create a valid subsequence of length n1. And because the entire array has XOR 0, we can't keep all n elements. Therefore, n1 is automatically optimal. Optimized approach. So our solution has only 3 cases. Case 1. Total XOR is non-zero. XOR not equal to 0. The entire array is already valid. Return n. Case 2. Total XOR is 0, but there is a non-zero element. XOR equal to 0. And exists number not equal to 0. Remove one non-zero element. The remaining XOR becomes that element which is non-zero. So return n-1. Case 3. Every element is 0. Then every possible subsequence also has XOR 0. There is no valid subsequence. Return 0. So we only need 2 pieces of information while scanning the array. 1. The total XOR. 2. Whether at least one element is non-zero. That's it. No subsequences. No DP table. No recursion. No backtracking. Just one pass. Python code. Class solution. Def longest subsequence. Self. Nums. List. Int. Dash. Int. XOR equals 0. Has underscore non-zero equals false. For number in nums. XOR caret equals number. If number has underscore non-zero equals true. If XOR return len nums. Return len nums. -1 if has underscore non-zero else 0. Let's walk through it. We start with XOR equals 0. This stores the XOR of every element we've seen. Then has underscore non-zero equals false. This tracks whether the array contains at least one non-zero value. Now we scan the array. For number in nums. XOR bitwise XOR requal to number. This continuously builds the total XOR. And if number has underscore non-zero equals true, means we've found an element that isn't 0. After the loop, we have the 2 facts we need. First, if XOR return len nums. If the total XOR is non-zero, keep everything. Otherwise, return len nums. -1 if has underscore non-zero else 0. If there is a non-zero element, remove 1 and return n-1. If every element is 0, return 0. Notice how little code this takes. The difficulty wasn't implementation. The difficulty was discovering the observation. Complexity. We scan the array exactly once. So the time complexity is O of n. And we only store 2 variables, XOR has underscore non-zero. So the extra space complexity is sad face of 1. With n up to 100,000, this is easily efficient enough. Interview insight. This is a great interview problem because the implementation is tiny, but the reasoning is the real test. An interviewer may ask, why is n-1 always enough when the total XOR is 0? Your answer should be, because if the XOR of the entire array is 0, removing one element x makes the remaining XOR equal to 0 XOR x equals x. So if x is non-zero, the remaining XOR is guaranteed to be non-zero. Then they might ask, why don't we need to find the best non-zero element? Because every non-zero element works. We only care about the length. Removing exactly one element gives us the maximum possible length once keeping all elements is impossible. And finally, what happens if every element is 0? Every subsequence still has XOR 0, so no valid subsequence exists. Pattern recognition. The bigger lesson here isn't just XOR. Is this, when the problem asks for the maximum length, first test whether the entire structure already satisfies the condition. If it does, keep everything. If it doesn't, ask whether removing the smallest possible number of elements can repair the condition. That's a powerful greedy mindset. And when you see XOR, remember these 2 properties. X XOR x equals 0. 0 XOR x equals x. Those identities often let you reason about what happens when elements are added or removed without explicitly rebuilding the entire XOR. So instead of thinking, which subsequence should I construct? Train yourself to think, what happens if I remove just one element? That shift is the real pattern. So the entire problem reduces to 3 cases. Total XOR not equal to 0. Answer equals n. Total XOR equal to 0. And some element not equal to 0. Answer equals n minus 1. All elements equals 0. Answer equals 0. The biggest takeaway? Don't brute force the subsequences. First, inspect the XOR of the entire array. If it's already non-zero, you're finished. If it's 0, one non-zero element is enough to break that 0 XOR. And that's why a problem that appears to require searching through exponentially many subsequences can actually be solved in O of n time, O of 1 space. Think in patterns, not brute force. That's the kind of observation that makes medium problems feel easy.